SwayamPrabha. Digital India. Educated India.
Okay, I think we will start now. In the last class we have talked about minimum fluidization velocity, that is one parameter. Now we talk about terminal velocities, because that also we should know, that is parameter number 5. Normally terminal velocity of single particles only we talk here. So, if you take one particle to have some kind of 3D effect, I just want to put this. Yeah. Good. Yeah, this particle is just falling through a fluid, right? Is a terminal velocity of single particle, where you take maybe very big tube, and then fluid is flowing through that, and you drop the particle. So, what are the forces that are acting on this? So, weight will be acting downwards, which is mg, and because it is coming down, drag will be acting in the opposite direction, that is fd. Yeah, fd, and you also have another force, buoyancy, fb. So, when all these three, w and these two are balanced, then you will get the terminal velocity, where it will initially when you put, you have acceleration and all that, then it reaches terminal velocity. From then onwards it constantly coming down. Okay? Yeah. So, we can derive this equation if we know all these terms, and the balance is fd drag force plus fb buoyancy should give you w mg. Okay. So, that is the one. Yeah, and the drag force is nothing but you have half rho ut square multiplied by the drag coefficient and the projected area. Okay. So, all three. So, if I have, that means drag force is directly proportional to the area. Okay. More the area, more the drag force. Okay. That is very simple one. And then of course, the kinetic energy. So, if I write that, you will have C d of rho ut square rho ut square into the projected area. Projected area of this is a circular area, because it is a spherical particle. So, I can write this one as pi dp square by 4, sorry, yeah, 4 plus buoyancy is the fluid displaced. So, that volume is dp cubed 6 into rho into my rho is becoming lousy, rho f into g, right. Yeah. Then this side we have mass into acceleration relative gravity. This again dp cubed 6, that is the volume, rho p is the particle, and then g is the that gravitational constant. Yeah. Okay. So, this is the one. So, if I rearrange this for ut, ut will be, okay, I will write here, ut is 4/3 dp rho p f into g by C d into rho. Okay. So, this is equation number 3, correct, no? What happened? Nila, something wrong? Okay, yeah. So, if I know C d, then I can calculate u t for any condition. Okay. So, again you have Stokes law regime and all that, you know what is C d for Stokes law regime, all that will be there, you can derive, but I am going to give one shot all the birds died. Okay. So, that is why C d given by Levenspiel and some other person called Haider, they gave C d for all regimes together. Okay. So, idea is I have to calculate u t, d p I know, rho p I know, rho f I know, because I am using you know some fluid which I know, particle size I know, particle density I know. So, all that I know, and g also you know, and only C d I do not know. So, for C d if we get a correlation, this correlation by that I will give you later, C d equal to 24 by R e p, where R e p is yeah, particle Reynolds number at terminal velocity. Okay. That u is u t, but R e p we are writing to say that it is particle Reynolds number. Okay. Yeah, this is 1 plus 8.1716 e power minus purely empirical equation. So, that is why you will have all funny powers phi s, yeah, this whole thing multiplied by R e p to the power of 0.0694 in the power only this one 0.5565 phi s, that is one term. Okay. Then I have here, how do I do? I think I can write here plus this continuation, plus I have 73.69 e power minus 5.0748 phi s into R e p, whole thing divided by R e p plus 5.378 e power 6.2122 phi s. This is the equation. This is equation number 4. Okay. I do not know how do you remember this. You have to remember. Right. Thank you. This entire thing. Yeah, good. Thank you. This thing too. Okay. Yeah, that's right. Thank you. You know that correlation or just like that you guessed?
No, sir, I couldn't understand how come that
24 by, okay. So, unless it is multiplied by that, yeah, true. This is the one, and I do not know how you are going to remember in the examination. So, I think this is the correlation which we have to use. If I give a problem to calculate u t, you have to use this correlation. Okay. So, this is given by Haider and Levenspiel, the same man, CRE man. This is powder technology, that is the journal name, and you have volume 58, page number 63, 1989. Were you born at that time? No, most of you. Okay, good. Yeah, then it happened only in your Jamana. So, I think this is the correlation. If you see the literature, there will be hundreds of UT correlations, but this is very well accepted one, because so much effort has gone into it is only to take all the data that is available till now, till then published, they have put into one correlation. Okay? Yeah, good. So, this is the equation, and as usual for complete spherical particles, you can reduce this equation to simple equation, where phi s equal to 1. So, this becomes a constant, and also this also becomes a constant. So, this becomes a constant. So, it is this also becomes a constant, it is a little bit simpler. Okay? Good. So, I think how many of you have Levenspiel book with you, 3rd edition? Yeah, wake him up. Yeah, I mean early morning, I think, how are you getting sleep, it is really surprising us. Early morning you just got, unless of course your early morning is 6 o'clock, 6 p.m. and this is the night time for you. Okay, I think you came from some other planet, already in the US. Okay, so that is why practicing US timings, sleep in the classroom and be moving in the night in the hostels, that is all. US, yeah, I was asking you something, what is that? Levenspiel book. Abhinav, you have the Levenspiel book with you? No? Very good. Yeah, why unnecessarily wasting time for chemical engineering or wasting money? Okay. Yeah, how many you said? How many, just lift again? Frankly, I am not going to check your room. Don't really deceive yourself, that is most important. Okay, you also have, Prabhu? He has always something different also. I think, my God, must be he is from, I think, Pandora. Yeah. That planet, Avatar. Always says, very good, yeah, e-book you have. How did you get e-book?
Sir, I think it is there on LAN.
So, anyone can download. I will tell Levenspiel. Okay. Sir, most of your books are, I think, misused, because hard copy is easy to read and e-copy is easy to store. Okay, you cannot even open unless you want to cut and paste something. If I give the assignment, cut and paste, and you can submit the assignment, no? That kind of thing. Yeah. So, in fact, this same equation and also UMF yesterday what we have discussed, there is a graph there in the 3rd edition. I think all of you should have 3rd edition. You belong to 3G generation, 3G section. Okay. So, that is why 3rd edition you will have, I have 1st edition, 2nd edition too, because I think I have seen 1G, 2G, now come to 3G, right. So, in the 3rd edition, CRE Levenspiel, in 3rd edition, what you have, there is a figure 25, chapter 20, figure number 5. This figure in fact gives one dimensionless number, that is equivalent to Archimedes number, versus UMF, UT, and there are many other things also in that graph. Okay, I think that graph also I have brought here to show, because you would have not never seen this graph. Okay. Yeah, if you know the x axis dp star, this dp star is, he has used some other dimensionless numbers. So, that will be Archimedes number. Archimedes number, all the information you know, g dp cubed, rho f, rho s minus rho f by mu square. So, rho f and mu are the fluid properties, rho p, dp are the properties of, yeah, and g is the property of this planet. Okay. So, all the things you know. So, you have that information, you can easily calculate and then read what is UMF or what is UT, okay, instead of solving. But anyway, this is not allowed in the examination, you have to use this equation to calculate if UT is asked. And who knows, tomorrow there may be surprise test asking this. Okay. Yeah, I know how to pain you, and you also know how to pain me, because I think you come here and sleep, that pains me. Okay. and you do not do any work, that pains me. And also immediately before even class started, sir, Ravi class, sir, okay, and no one tells the sir, Krishna has class, sir, okay. So all these things, you also pain me in the equal direction, are reversible reactions, okay, good. Anyway, so this is the one which is a very good figure, where he has nicely beautifully put that, and he has also given in this figure what are the possible ranges of operation, what we have done, normal fluidization, fast fluidization, pneumatic conveying, all that regimes are given here, wonderful graph, okay. But I think assumption is that you are interested, that is why I am telling. I think you think that I am a madman, right. So generally this fellow talks something, I think which we come here and happily sleep, that is enough for me, okay. So that is the kind of attitude if you have, what do you learn, I say, what anyone can learn, no one can learn anything. So this is the problem. Yesterday we had 1.5 hours, 2 hours discussion about JEE, okay, and none other than the DST chief, I think next to minister he is in this scientific thing, Dr. Ramaswamy, he came and spent so much time, and I was thinking that why the hell in our country we should have, I think I believe Mao very strongly. You know who is Mao? You don't know Shivakumar? Mao, who is Mao? Chinese something. What is this? Chinese animal or Chinese horse or Chinese dog or what? Huh? Chinese man? Huh? Chinese student? Chinese food? Noodles we know. That we know very well. Yeah. Mao, once he came to the power, he found that many people are not concentrated in academic institutions. So then he closed all the academic institutions and then said that you have to go and produce wheat. That is all, sent to fields. Okay. So I mean, some people say that no, the entire academic intellectuality gone and all that, but I feel that is more practical, because if someone is not interested, why should we spend time on that? Okay. So I mean, yesterday so much discussion about this JEE, how to improve, how to increase the interest in the students. Where is the interest, I say? Once the JEE is passed or once any entrance examination is passed, you think that life is settled. Okay. Any entrance examination, it may be T set, K set, T set, F set, M set, many sets, everything there is set only. Okay. Once that examination is over, then life is settled, because you do not have to do anything. And what do you do in the school? All the time there is no school for you anyway, it is only coaching centers what you have seen. Okay. So I think that beautiful life of school gone, now he wants to bring back that school education to some extent. That is why I think board they want to have some 40% marks, okay, that school marks. In fact, we had that excellent time, we had really excellent life. When we were students, no one used to tell that you read or do not read. That is all, very happy. While going also, I mean, I have to walk nearly 7 kilometers every day to go to school, another 7 kilometers to come back. So on the way, all happy walking, happy running, happy playing and all that. Okay. And then you come here and then there is no power anyway. By the time you come, it will be 6 o'clock or so, eat food and then eat and then sleep most of the time. Okay. But for us, 1 year examinations and all that, not for every day 10 tests like coaching center, okay, or 10 or 24 tests, because every hour a test in coaching center. Okay. Every hour a test, finally I think you don't know what to write at the end. Okay. So everything technology has become technology, totally beautifully converted. Technology has been technology now. So that is why in Hyderabad, I do not know whether I told you, I think I told you last semester also this, I think maybe Abhinav, all these people may be knowing this, or at least they will come to know about this. In Hyderabad, Hyderabad, 50% of the Hyderabad in the US. Yeah, I think every family, every hut, every building, every 5-story buildings, all these people, I think in any place you take, there is one person who has gone to US from Hyderabad. So I think that person stayed there for 5 years or so, he came back here to marry, okay, because I think after finishing BTech or something he went there. After coming back, and then he saw 4 girls, and he does not know how to choose, right. So then father knows his strength and weakness or anything. So, then father what he said is okay, first girl A, second girl B, third girl C, fourth girl D. Then he knows to tick, yeah, fourth D. Till then he does not know how to tick, how to choose. So, that is how we have converted all our younger generation to technology to technology. That is what I have been telling, technology. Okay. So, like that I think unless that ABCD is there, you cannot do anything. You go to your mess, and if it is idli, dosa and upma and all that, you do not know what to take. If that fellow writes A, B, C, D, tick and then take. That is the kind of life we have here now on this planet, particularly in India. Okay. So, then what is the interest for you? Absolutely there is no interest, no. I mean, like a mad fellow, I will be talking here very enthusiastically, thinking that oh my God, entire thing is fluidization, the whole universe again is only fluidization. So, that kind of thing I will say. But you come here and then happily sleep, okay, and then otherwise you go to your own matrix, searching for Neo and searching for other, what is our name? In the movie you have seen, no? Trinity, yeah, good. He woke up now. He is in matrix, so he knows Trinity is he is inside the matrix, yeah. Trinity, or an old person like me, what is his name? Morpheus. Morpheus. And I think the names also are very good names, Switch. Switch is one person's name, Switch connection. So, like that is a very wonderful movie, I say. Yeah. Okay, good. So, this is about terminal velocity. The next point is, in fact, terminal velocity also there is a lot of information. And when we tell about this particular thing, completely we are in a ideal world. Where is one particle? When do you use one particle in chemical engineering? You never use except on the board. Okay. Even if you go to lab also, I think you will have a number of particles. But in reality, you will have again some other thing, which is called transportation velocity and all that. I think that will come later when you really take a fluidized bed course. Okay. But I think here it is only an indication for us that what is the maximum velocity that may be possible for fluidization. That is why we need this parameter. Okay. The next one is bed height, right? Or you do not know? Static bed height. Yeah. What is the static bed height? We use, what is the number? 6. Static bed height. Okay. See, every time I will tell what I have been telling all the time to you is only to make you again temporarily come back to the class. That is why I tell that you do not have interest and all that, so that at least okay, at least this fellow is telling at least 10 minutes, let me concentrate. So, that is the reason. Otherwise, you may think that this fellow is pessimistic, always talks like that. No, whenever it is trying to go away from the track, slightly applying some force to bring it back to the track. That is why I do not know any other force except telling this. If you have any other information, tell me, I use that technique. Okay, how to bring you to the class. So, otherwise I do not know. I think that is why every time I will point out the moment I think that you are not concentrating. Okay. So, that is the reason. Prabhu, any comments? You will give a one wonderful comment. No comment, huh? That itself is wonderful. Okay. So, usually Hp by d static bed height, okay, is normally 1 to 2 best fluidization or good fluidization, we do not say best, good fluidization. Okay, best fluidization means all the particles should be very, very spherical and all the particles should be exactly same size, all this that we do not get normally. So, that is why. Okay. This is good fluidization. What do you mean by good fluidization? If someone asks you what do you mean by good fluidization, what do you say, Kavya? When do you say you have good fluidization?
There is no sucking or pinching.
Yeah, what is the meaning of that? You are only telling the other opposite quality you are telling, so that if everyone is lousy, I am very good. Okay, that kind of thing. Okay, not that. I mean, really, Abhinav?
Good mixing in solids.
Yeah, that means good contact between, not mixing. Yeah, mixing also you have without good contact also, because when you have bubbles and all that. So, uniform fluidization and also good contact between solids and gas. That means each and every particle must have very good contact with the fluid, okay, either gas or liquid. That is what we mean by good fluidization. Okay. But when you have Hp by d less than 1, you have what is called shallow beds. So, in the shallow beds generally you will not have good contact, because there is no time for contacting, because you take only 10 particles height. Okay. If you have 1 mm particles, 1 mm is very large for fluidization, but easy visualization, that is why I am telling 1 mm. So, 10 mm bed height you put, even though diameter is 1 meter, those are shallow beds. 1 meter diameter also, if you have only 10 particle height or 20 particles height, then that is very shallow bed. Okay. Under some circumstances shallow beds are preferred if you avoid bubbling, because there is no time for gas to bubble to grow. Okay. So, that is why shallow beds are used sometimes, particularly for drying. It also can be used beautifully for drying. Okay. And they call this fluidized bed plug flow dryers. Fluidized bed, we know that it is a mixed flow. How can you have plug flow? Not in gases, solids are. How can you make this mixed flow as plug flow?
It is shallow, but
It is shallow, but I think
there won't be the time for the gas to go to it, so it will be plug flow.
how can it be plug flow? Because I think even then they are bubbling, no? I mean, they are mixing. You increase the length, okay, and then put the solids here. This is just a plate with the perforations, maybe with a slight angle for flow. Okay. Even you do not need a slight angle, but better to have if you want better flow. Otherwise, even if you put horizontally also, you are feeding here all the time, and it may be 2 meters length, right, straight channel, and bottom you have the perforated plate, and you uniformly distribute throughout the channel the air, hot air, and the wet solids are put in one corner. So, those particles will slowly dry there and then start moving. So, till then of course, there may not be any flow there. Once it starts moving, then from there continuously it comes out, and then you can collect the solids there, and the length is designed for how much drying you require. Maybe end moisture may be 1%, 2%, 5%, 10%, depending on your requirement. But drawback here is that you cannot use 50%, 60% moisture. It is a tertiary treatment for tertiary drying technique. That means, first you may if it is completely paste, what do? You cannot use any column except tray type dryers. Okay. Then once it is dried for some time, then you will have some moisture where the particles are not sticking, but a little bit flowable. So, at that point of time you switch over to this, and if that is not sufficient, then you use some other drying technique. There are so many drying techniques. Okay. So, then the final one, when you want to have only 1% and all that, fluidized beds are excellent, particularly plug flow dryers. What is the advantage of plug flow dryers? Because each and every particle again will have exactly same moisture content. In fact, you use this nylon and all that shirts. Yeah, for polymer drying, particularly when they want to make this rayon and all that, for making this cloth, they first make the polymer granules, and they have to be very accurately dried. That means, each and every particle should have exactly same moisture content. It seems if this moisture content is slightly different in some particles, okay, in some other particles whether low or high, then the thread will not come properly, it seems. Okay. So, that will not come properly. So, that is the reason why they use these plug flow dryers for polymer drying when you want to use that one for textiles. So many advantages. Okay, good. So, this is the one, that is all what we, I think another one is, of course, if Hp by d greater than 5, what do you get? That means, you have not seen at all, you just look what I have told 2 classes back, one narrow column and then slightly more thing, it is slugging. That means, the entire bed is occupying, the bubbles are occupying the entire cross section of the bed, slugging. But that means, if the initial static bed height itself, if you have 5, and then of course, generally when we say this condition, slugging means narrow construction, narrow cross section, then you get the slugging. Okay. I mean, what I said was true, I say. I think all of you are Gajnis only. Yeah, I do not know when you remember, maybe I think that Gajni at least fellow after 15 minutes he remembers. something, but here I think there is no remembrance at all, maybe just examination before the examination you may remember. Okay, good. So, that is static bed height, and the last one is 7. Yeah, Bela, you have heat and mass transfer correlations. Yeah. Heat and mass transfer correlations. All these things we require before we start the reactor models. So, that is why, yeah, here you have again correlation. So, there we cannot discuss much unless how do you develop these correlations. When you go we can discuss, but we do not have that much time, but simply we accept these things because they are already available, and those who are interested anyway they can definitely go and then read all this information. How do you develop this? J d equal to J h equal to save the students, I think they have given nice correlation for both one. Okay, this is d p g mu into 1 minus epsilon whole to the power of 0.44. That is 1. This is also equal to 5.7, same number, d p g mu by 1 minus epsilon. This is to the power of minus 0.78. Yeah, and the condition is this is less than 5000, and this is d p g by mu into 1 minus epsilon less than 30. Yeah. So, what is that I have? Equation number 4. I think here we do not have to give this equation number. This is 6, this is 7. Okay. Renita, do you remember what is that number called? d p g by mu, is it dimensionless? Reynolds, question, Reynolds? No. Answer, huh? Yeah, why is that a dimensional number? What are the units of that? What is d p? What is g? What are the units of mass flow rate? Kg per second. Yeah, you put kg per second and then try to get dimensionless number. Yeah, mass flux. Okay, mass flux. Okay, we call also mass velocity sometimes, but it is mass flux. So, kg meter square per second. This is one of another some question which I ask in PhD interviews and all that. Give 2 or 3 different forms of Reynolds number. It is not always u rho d p by mu. This is also another one. What is the other form? There is another form. dp that is bottom, but in the numerator what do you have? dp by nu, du by nu. Okay. So, where nu is so at least know that there are different forms. Okay. Yeah, good. So, this is the correlation what we have, where of course, here you see void edge is the one which has been used, right. These are empirical correlations, very old correlations, but if you see the literature again you will have lots of correlations available for. Yeah, and of course, JD definition, do you remember? Kg by u 2 by 3, very good, excellent. Okay, JD equal to k by u or kg by u, Schmidt number to the power of 2 by 3. Okay, good. Can you also tell me in terms of another dimensionless numbers, JD, not k by u, not f by 2, not standard number. you also have actually that same thing k by u or kg by u, Schmidt number to the power of 2 by 3 can be also written in terms of Sherwood number, Reynolds number and Schmidt number. Do that exercise, you will know that. I do not want to write there. Sherwood number, Reynolds number and Schmidt number again, of course. Yeah. That is the original definition, J d equal to, in terms of dimensionless number, all dimensionless numbers. Okay. The problem there is why we cannot have kg by u, kg will have some other units, u may have some other units. But when you make that as a dimensionless number, group of dimensionless numbers, then you do not have to really worry. So, that is why originally old people have done that. Okay, good. So, that is the one, good. So, now all the parameters are over. There are many correlations available. Okay. So, but still these are the some, again here you are very nice students, you never ask questions. So, I have to ask questions and I have to also answer. Okay. When I say this J d equal to J h mass transfer or E transfer, you never told me where is this mass transfer going, sir, from which place to which place. So, this transfer should be from one to the other, no? Which one is transferring what? We have here gas phase, or if we have fluid phase and solid phase. This is mainly for gas solid fluidization, that you have to note down somewhere, because for liquid solid applications are so less, most of the information is given in the literature only for gas solid fluidization. Okay. Yeah. So, that is why this one, if I have particles, from particles to, if hot particles are there, you want to cool them, then you send cold air. So, then some of the heat that is there in the particles is taken by the gas will go. Okay. So, similarly, if you want to heat the solids, then you have to use drying, like not drying, sorry, heating, hot air you take, right, and then send fluidize cold particles, they will get heated up. So, those particles may be used somewhere else in the process. Okay. So, these are the things what we have, and of course, as I told you, these fluidized beds can also be used as combustors, coal combustors, where they use power generation. Power generation they use coal combustors. Fluidized bed is used as the combustor, where coal is fluidized and burnt. If you go for beyond 650 degrees or 700 degrees centigrade, it catches fire if you have sufficient oxygen. So, then it burns and you have to extract that heat. To extract that heat, you put inside cooling coils with the water. So, that water will become steam, then steam will go through steam turbines, steam turbine will be attached to generator and generator will give us AC, DC, whatever, these lights and all that. Okay. So, there the heat transfer is from solids to, because coal particles are burning and they are at high temperature and you have the cold liquid and water going inside. So, the heat transfer is from solids to pipes, the tubes where you have water. So, finally, it has to cross tubes and then reach water, and water will get steam, water will become steam. Okay. So, those are the things. So, now we have to go for reactor models, that is 8 reactor model, that means fluidized bed reactor models. Okay, I think I will tell you the story, I think quickly, so that next class I think we will have, because if I draw that figure it may take some time. Okay. So, that is why you do not have that time, you have to do now, right. Yeah. The story here is that in the reactor models, what they did was they have taken the conversion available in the literature for first order reactions, okay, and they have even taken the same first order reaction, one particular reaction, and then collected data from someone publishing from India, someone maybe from Germany, someone from Japan or UK, US, all the data they have plotted, same reaction, same catalyst, same temperature. So, when they plotted there in that graph, the points are throughout the graph, like our cricket field. Okay. Throughout the graph you have the points, that means there is no particular trend, there is no particular trend for the behavior of conversion. What they plotted was conversion versus for first order reaction, what is the natural number that comes as x axis. For batch reactor normally you use time, Damkohler number. What is Damkohler number for first order?
tau c
k tau, where k is the reaction rate constant and tau is space time. Okay? Yeah. So k tau versus x, when they plotted, the entire graph has different all the particles and the same for the same reaction, same catalyst for the same conditions. Then they have also drawn theoretically what is plug flow line on that, theoretically what is mixed flow line on that, because we know only first two reactors, ideal reactors what we have, right. So, when they theoretically they could draw those lines, these are experimental points. So, they found that the conversion is even much less than mixed flow reactor. Now, we know that in the extremes, one is infinite mixing, another one is zero mixing. Zero mixing for n greater than 0 reaction will give me always higher conversion for a given volume, okay. And whereas mixed flow is the worst, it will give the least conversion for a given volume, least conversion for a given volume. So, now I think fluidized bed is behaving much worse than that, much worse than worst reactor. So, then they thought that what is really happening, because you cannot, no one expected that this much conversion, low conversions you will get in a fluidized bed, because what is our assumption? Our assumption is that fluidized bed is equivalent to mixed flow contacting wise. So, then what is the natural tendency for anyone to try whenever you want to model, you have done the experimental work, how you start your data analysis is that whatever you know first, the ideal reactors first, that you check. If you found out, if you find what is the conversion for various Damkohler numbers, you just try to put that in the form of either mixed flow reactor or plug flow reactor, because those are the ideal reactors. If they are not properly able to predict this conversion, experimental conversion, then what do? You will go for what are called one parameter models. What are one parameter models? Axial dispersion model, tanks in series model. What is that? One more. So many times I have drawn this last time in the, I think here also once I think probably I would have written recycle model. Recycle also, recycle infinity what? Reactor, mixed flow, recycle 0 plug flow reactor. So, all the extremes are covered with axial dispersion and also n number of tanks. When n equal to infinity you will have plug flow, n equal to 1 you have mixed flow, dispersion number equal to 0 plug flow, dispersion number equal to infinity you have mixed flow. That means, anywhere in between mixing also you can now try to imagine. This is perfect mixing, this is 0 mixing, some intermediate mixing can be imagined with this one parameter model, with R recycle, with dispersion number and with tanks in series. Okay, they tried that. When they tried, that also did not work. Then what is the next logical one? Compartment models. Okay, it is not just axial dispersion that is coming. Now, let me imagine that I have axial dispersion plus channeling, dead space, all these. So, even when they put these compartment models, assuming more parameters like dead space for solids or dead space for gas, channeling for gas, all that combinations, these are all called RTD models, okay? Residence time distribution models, where we have studied in the, I think even you would have definitely studied, you have done RTD, no, residence time distribution. Yeah, definitely in that Preeti would have told you, Preeti only taught you, right? Yeah, definitely she would have told this, because she is also very much interested in CRE. So, all compartment models you try to use, and those compartment models also did not work. That means, all these models are not able to predict what is the conversion that is coming out, and particularly when you go for 1 inch diameter, then you go to 2 inch diameter, okay? Totally different conversions, right? Or otherwise you change the particle size, totally different conversions, same conditions same, but instead of using 10 micron particles you may use 100 micron particles, then again changes, okay? So, even distributor plate, you change the distributor plate, perforated plate, or instead of perforated plate you may have now porous plate, you change that, again conversion changes. This has become a big mystery. What do you really do to understand what is going on in the fluidized bed? Okay? So, I think that we will discuss in the next class, what is really going on in the fluidized bed. Okay, suspense, like our serials in the correct time, but you never bother anyway. Whether it is suspense or no suspense, it is same for you. Okay, but what happens next time, I mean in the next class, only I will be excited, but you will not be, you will be sitting there. I want some dead space here, so that is there. Okay, yeah. Again, that is very interesting how they have done it. I think really wonderful models they have developed, and how much thinking has gone into that, you will know when I explain that how they really developed the fluidized bed models. Okay, good. You have to run. Okay, thank you.